First, I would like to introduce the Meteor project, which enabled the creation of this video. Meteor stands for Modeling Exposure through Earth Observation Routines and was funded by the UK Space Agency through their International Partnership Programme as part of the Global Challenges Research Fund. The Meteor project aims to develop innovative applications of Earth observation technologies to improve understanding of exposure. Natural hazards have had escalating impacts, which are contributed to by an increasing exposure of population and assets. However, a major challenge when making disaster risk management decisions can be a poor understanding of the distribution and character of exposure. Robust quantitative methods are required to justify these decisions, and in this project we are looking at the use of Earth observation technologies within that context. Within the Meteor project, there is also the aim to share knowledge. This video is produced as a part of a series of educational videos to enable the use of Meteor products and data. The following slides will focus on the implementation of the landslide susceptibility and landslide hazard assessment in a GIS environment and will cover a short introduction of the modeling tool, a reminder of the model input data workflow, two examples of deriving and implementing fuzzy functions for continuous-based and categorical variables, and finally, the model diagrams of the resulting susceptibility and hazard maps. I should mention these slides focus on rainfall-induced landslides only. However, the modeling process is similar for earthquake-triggered ones. To implement the landslide susceptibility and hazard assessment methodologies in a GIS environment, we use the Model Builder tool in ArcMap application within ArcGIS. Model Builder is an application used to create, edit, and manage models. Models are workflows that string together sequences of geoprocessing tools, feeding the output of one tool into another tool as input. A simple application is illustrated in the right-hand side figure, where the model executes a clipping operation using a given reference area, adds a field, and then calculates a value for the new field. This operation is executed in a single workflow of one iteration. While Model Builder is very useful for constructing and executing simple workflows, it also provides advanced methods for extending our GIS functionality by allowing us to create and share our models as tools. Model Builder has the benefit of being easy to use for creating workflows containing a series of tools, and it is compatible with other applications through scripting. For more information on how to use Model Builder, please check the ArcMap documentation available online or directly through the installed application. The data workflow used in Model Builder to create the landslide susceptibility and hazard maps uses a number of interdependent elements. First, the landslide susceptibility predisposing factor or predictor classes are assigned weights through the frequency ratio analysis and expert elicitation. These weights are used to define a rule set for each predictor, which is in effect a description of the relationship between a landslide's spatial likelihood and each predictor class. This qualitative description is then translated in quantitative terms through function parameters, which are finally used to define a fuzzy membership function. There are two basic model functions depending on the type of variable or data associated with each predictor. The upper one, A, for continuous data, is where EIJV is the value of predisposing factor V at location ij, as in function A, and W1V, W2V, and WMV are the corresponding landslide susceptibilities when factor V takes the value of C1V, C2V, and CMV. For more details on the fuzzy inference methodology, please consult the papers of Zhu et al. 2008-2014, referenced at the end of this presentation. Taking an example for each type of variable, we start with a fuzzy function definition for continuous-based variables, such as slope gradient. The frequency ratio allowed us to assign weights to each slope class and identify the type of function applicable for this predictor, which in this case is a bell-shaped function. The rule set definition for this predictor states that susceptibility is at maximum for slopes between 15 and 35 degrees, As the slope decreases below 15 degrees and increases above 35 degrees, susceptibility decreases at different rates. Knowing the shape of the function and its rule set description, the parameters used for defining the fuzzy function can then be selected. In this case, the bell-shaped curve was split in two parts, one for the left, akin to an S shape, and one for the right, similar to a Z-shaped curve, with different parameters for each side as indicated here. For example, susceptibility is assumed to be at crossover, that is equal to 0.5, when slope gradient is equal or greater than 45 degrees for the right side of the curve and equal or smaller than 15 degrees for the left side of the curve. These numbers are then transferred in their corresponding fuzzy function and implemented in the model builder. Model builder uses a model diagram to stream and visualize the entire process. The diagram in this slide is composed of the following elements. In blue, the input parameter, in this case the slope map with values in degrees. In yellow, the tools, here the raster calculator in which the fuzzy function is implemented sequentially, and finally in green, intermediary or final outputs. This particular model diagram contains 14 processes embedded in a single iteration. The model tool and raster calculator dialog boxes on the left-hand side of the screen are used to create and execute the fuzzy function as an algebraic expression that will output a raster. The results of this processing are illustrated by the fuzzy slope map here, where after the application of the fuzzy membership function, each pixel takes the value from 0 to 1, reflecting the certainty degree of membership to landslide susceptibility, with 0 meaning not susceptible and 1 susceptible. In a second example, we used lithology to illustrate the implementation of the model for categorical variables. After the analysis of the frequency ratio results, the rule set definition states that the most susceptible geological groups are those with fractured or tectonized rocks and mixed lithologies, typically foliated, bedded, and prone to weathering. The least susceptible is the Himal group gneiss, as indicated by the weights attributed to each class in the following function and instructed in the model builder diagram shown here. The resulting fuzzy lithology map shows each pixel associated with the lithology class taking the value indicated in the fuzzy membership function, which is the weight resulting from the frequency ratio and expert elicitation analysis. Lastly, Model Builder is also used to derive the landslide susceptibility and hazard maps. For landslide susceptibility, the raster calculator dialog box shows the aggregation function described in step 5 of susceptibility assessment methodology, while the model diagram illustrates the use of 7 fuzzy predictor maps as input parameters. The modeling output is illustrated in the right-hand side figure. The model for landslide hazard assessment takes into account 2 input parameters, the extreme rainfall data, and these are multiplied as indicated in the raster calculator box on the left-hand side. The resulting hazard map for rainfall-induced landslides is depicted in the adjacent figure. For more information on the landslide susceptibility and hazard assessment methodologies, please revise the provided training material and references.